Okay, so we were doing Walther Pohl chapter 1. This is the part 4. In this process, the residual sulfide retains the precious metals which it may bequeath to a later batch of undersaturated magmatic melt. Most orthomagmatic ore deposits are found in intrusive rocks. Eruptive equivalents are also notable, such as the nickel, copper, iron sulfides and chromatic lava flows of Archean greenstone belts or the magnetite and hematite lavas and two andesitic rhyolitic volcanoes in Chile, Mexico, and Pakistan. Basic shapes of orthomagmatic ore bodies are layers in stratified magmatic rocks, often formed as cumulates, lenses, or cross-cutting dikes and veins. This depends on the morphology of the segregation, sedimentation surface, and on the dynamic factors. Massive ore is the product of highly efficient unmixing of ore particles or melt droplets and silicates, whereas disseminated mineralization reflects lower efficiency. Highly complex ore body shapes can be found in flow channels and pipes of mafic lavas and intrusions. For example, when widening or curvature of flow tubes induce lower flow velocity of silicate melt that carries chromite crystals or sulfide melt droplets. Okay. Textbook examples of orthomagmatic deposits are sulfide, iron, nickel, copper, PGE ores hosted by Archean chromatic lavas of the Yarran Craton in Western Australia. Gravitational settling can also explain many features of ore formation in rare mafic intrusions. Other contributing processes include fluid differentiation and convecting scavenging. Okay, fluid differentiation and convecting scavenging. In situ crystallization on the floor of the melt body, mixing of two different melts and uptake of material from outside. Example by melting siliceous or sulfur-rich host rocks. Often the formation and segregation of a sulfide melt is the key to enrichment of exploitable metals. Layered melt bodies in respect of composition, temperature, and density. Orthomagmatic nickel sulfide ore in pegmatites. Pegmatites are ultramafic volcanic rocks with healthy temperatures of approximately 1700 degrees centigrade, containing greater than 80 weight percentage in G. Their formation is a consequence of mantle temperatures approximately 100 degrees centigrade higher than today. Chromatic melts originated by 30 to 50% partial melting of mantle. Normally, these melts remain sulfide undersaturated from extraction through ascent and eruption through emplacement. These melts remain sulfide undersaturated from extraction through ascent and eruption through emplacement. Okay, liquid chromatite lavas had a very high temperature and very low viscosity, similar to water, resulting in high flow velocities. Chromatite lavas are capable of eroding and melting most volcanic and sedimentary wall rocks, ground melting, or thermochemical erosion. The flows followed troughs on the seafloor and formed flow tubes similar to submarine basalts. Stomatites were typically charged with suspended or living crystals. During cooling, cumulates and vesicular textures formed because of the extreme temperature difference between ocean water and magnesium rich melts. Flow drops are characterized by skeletal growth of olivine and pyroxene spinifex texture. Elongate massive sulfide bodies, which were clearly formed from liquid sulfide melt, occur at the floor of flow tubes and create upwards into disseminated matrix or net textured ore. Ore textures reflect gravitational settling in the liquid phase. Sulfide melts can only form upon sulfur saturation, implying high sulfur content. Sulfide melts can only form upon sulfur saturation, implying high sulfur content. The common association of sulfide mineralization with the presence of sulfur-rich interflow sediments and isotopic compositions of sulfur are strong arguments that admixture of crystal sulfur is the main difference between fertile and barren chromatites. Okay. Uh, So strong arguments that admixture of crystal sulfur is the main difference between fertile and barren chromatites. The availability of nickel and elements such as platinum for availability of nickel and elements such as platinum for partitioning into sulfide, iron sulfide melt is favored by low redox conditions. In that case, nickel is dissolved in the silicate liquid as NiO, Ni0 and no charge, and is not available for incorporation into olivine. Apart from the redox constraints, nickel content of magmatic sulfide liquids is largely controlled by partitioning equilibrium and mass balance between sulfide, silicate and sulfide melt, the R factor. Okay. Including dynamic factors such as mixing and redissolution. The ore minerals of chromatite nickel deposits comprise pyrrhotite, pentlandite, chalcopyrite, and pyrite, with nickel concentrations in ore reaching 20%. Prendergast describes the nickel-bearing chromatites of Zimbabwe as proximal and basal parts of submarine volcanoes that were quite flat and extended over hundreds of kilometers. The new Archean chromatites of Western Australia 2.7 to 2.9 Ga host the majority of the world's chromatite associated nickel copper PGE deposits. Paleo-Archean chromatites are depleted in platinum group elements PGE because the metal source of the younger metalliferous chromatites, that is cosmic matter bombarding the earth during the period of 4.5 to 3.8 Ga, was only gradually mixed into mantle. Meyer et al. 2009. In contrast to Western Australia, the closely comparable Abitibi Greenstone Belt in Canada is richly endowed with volcanogenic massive sulfide deposits. Skid Creek, Noranda, both regions display abundant orogenic gold deposits. It is assumed that the disparity is due to different lithospheric structures. Barnes et al. 2007. Random spinifex texture, fluty spinifex texture, there is comatite lava flow, thermal erosion trough, aphelic zone, interpilosulfides. The orthomagmatic core formation in the Bushveld complex. The Bushveld intrusive complex comprises the Rustenburg layered suit and the Lebova granites. Okay. Uh, the first term designates the layered mafic ultramafic intrusion, which was formed in the Paleoproterozoic at approximately 2054 million annum and which contains enormous metal resources. The granites have nearly the same age and host less important fluorite and tin deposits. The roof of the Bushveld complex and the overlying granites consist of thick precursor basaltic andesites to rhyolites. The Ruiberg group volcanics. Ruiberg volcanics and intruding granites are the products of crustal melting caused by the giant mass of hot mafic melt. Country rocks of the Bushveld intrusion are Paleoproterozoic sediments and volcanics of the Transvaal supergroup and Archean basement. The Rustenburg layered suit reaches a thickness of 9,000 meters. It is strongly layered at all scales. The major unit from bottom to top comprise the lower zone with dunite, bronzitite, and harzburgite. Conspicuously banded critical zones, the lower part of orthopyroxenite, chromatite bands, and some harzburgite, and the higher part marked by the first cumulus plagioclase and by cyclic layering of economically significant platiniferous chromatite, Habsburgite, bronzitite, nodite, and anorthosite in this order, cyclic units. Its upper boundary is marked by Merensky Reef, platinum, nickel, and copper. Okay. The main zone is with gabbronorite and minor layering the upper zone with magnetite, ferrocablo, and ferrodiorite, which contains numerous magnetite, that is, vanadium and titanium layers. So, marginal zone, lower zone, critical zone, main zone, upper zone. We will keep it till this much and continue in the next part.